Hello, my name is Bill Robbins. In this video I'm going to talk about gate turnoff thyristors, or GTOs for short. I'm going to talk about the following topics. First, their basic structure and IV characteristics, and then the physical operation of GTOs, especially the turnoff operation. Then I'll talk about the switching behavior of the GTOs, the IV characteristics as a function of time. And then finally talk about a couple of derivatives of the GTO, the so-called GCT and emitter turnoff thyristors. Going to the first topic, which will be on the next slide. This slide shows a picture of the basic GTO structure. It has the four-layer structure, PN, PN between anode and cathode as the standard SCR. However, there are a few adaptations in order to make the gate capable of turning off the thyristor. These adaptations include, one, this mesa structure for the cathode area, in which the gate is somewhat lower in vertical dimension compared to the top of the cathode structure, and very close spacing between these mesas, so we have a highly interdigitated gate cathode structure, which makes it easier for the gate to turn off the thyristor by means of a negative gate current. These etched cathode islands also make it easier to make contact to the outside world because this top of the mesa has a metallization which is then in mechanical contact with a thick copper plate. And finally, some GTOs have what is called an anode short at the other end, where we have an N+ region every so often that punctuates or punches through the first P+ layer. This structure speeds up the turnoff capability of the GTO, as I'll explain somewhat later, and as a consequence of this N+ structure, the GTO with an anode short has no reverse blocking capability, because if there was a blocking capability, it would be this junction J1, because junction J3, which could be a blocking junction, we know has a very low breakdown voltage because of the fairly heavy doping on the N and P-type sides, as we discussed earlier when we were talking about the standard SCR. The GTO symbol is shown down here below. It looks like the standard symbol for a thyristor with the exception of the two parallel lines here in the gate area. Those two lines, which have arrowheads indicating both positive gate current going in to turn it on and negative gate current coming out to turn the device off. Going on to the next topic, where we concentrate on the physical operation of the device. The GTO is basically a standard thyristor in the sense that we use the same two transistor model to describe the basic operation of the GTO. So I won't go into a general discussion again about the overall operation of the GTO. I just want to concentrate on the turnoff operation. In order to turn off the GTO, we have to pull one or both of these transistors out of saturation and into the active region. Once we get them pulled into the active region, we know that's an unstable region of operation, and the disturbance that initiated pushing the devices into the active region, because of the instability there, the devices will then turn themselves into cutoff and thus turn off the GTO. Now, in a standard transistor circuit, the way we can pull a transistor out of saturation is to force the base current to be less than the collector current divided by the beta of the transistor. In terms of the transistor Q2, that means we want IB2 to be less than I sub C2 divided by the beta of that transistor. We can express that I sub B2 in terms of the terminal variables, the anode current and the gate current, by means of the equations in the line that I just checked. And if we then take those two equations and do a little bit of algebra, we finally get down to this line where we can express the gate current having to be less than the anode current divided by a constant. That constant is a so-called turnoff gain and is given by beta off is equal to alpha 2 divided by 1 minus alpha 1 minus alpha 2. In case you have forgotten, alpha is the so-called base transport factor of the transistor. It represents that portion of the electrons that are ejected from the emitter into the p-type base of an NPN transistor and survive recombination to be collected at the collector. A good transistor has an alpha on the order of 0.98 or 0.99. And there's a relationship between the alpha of a transistor and its beta. Alpha is equal to beta over beta plus 1. So what that means is, in order to have large turnoff gain, we need to have alpha 2 about equal to 1 and alpha 1 much less than 1. We make alpha 1 small by having a wide base region for the N1 region, that's the base of Q1, and we also know that that is needed in order to have a large blocking voltage. We also need a short lifetime in the N1 region to remove excess carriers fairly rapidly, and that also contributes to a small value of alpha 1. However, there is a trade-off. A short carrier lifetime in the N1 region means higher on-state losses, and so what we would like to do is to be able to break this dilemma between higher on-state losses and the desire for fast turnoff. The anode shorts that I was talking about help to resolve this. The anode shorts act as a sink for the excess holes in the N1 region. The lifetime in the anode short itself can be very, very short, and so in the immediate vicinity of where the anode short makes contact to the N1 region, we're going to set up a very steep gradient of carriers because of the recombination being very fast at that interface, and thus we will pull out excess carriers by diffusion, the excess holes, toward those anode plugs more rapidly, and thus overall the effective lifetime has been reduced. Making alpha 2 equal to unity is what we would normally do to make a good transistor, and we do this by making the P2 layer relatively thin and heavily doped, and the same thing that we would normally do for a good transistor. And finally, we use a highly interdigitated gate cathode structure in order to minimize the cathode current crowding that could result if we had a very long distance between the center of the gate metallization and the center of the adjacent cathode metallization. And we talked about this when we were talking about current crowding in a standard thyristor. Moving on to the next slide, part of this discussion has to take into account that there is a maximum controllable anode current. I show here a diagram of a cross-sectional view of one of the gate cathode regions, and in this instance we are pulling a negative gate current in the direction that I've shown here. One of these two current paths are indicating negative gate current, and the negative gate current then is pulling out excess carriers from the excess carrier density that we have in the base region of the Q2 transistor. And by doing this, we are interrupting the flow of current to the Q2 transistor, and thus making the base current less than what is needed in order to keep the transistor in saturation. Well, this works up to a point. However, if we have very large negative gate currents, which we would like to have in order to minimize the amount of time it takes to pull out that negative charge, we run the danger of a breakdown voltage being developed between the gate and the cathode. And the reason for that is as shown here in the lower part of the picture, where we have this resistance that represents the lateral voltage drops that can develop if we have very large gate currents. Since the breakdown voltage of this junction is fairly small, it is possible that with enough current density flowing between the gate and the cathode in the directions that I've indicated, we may cause breakdown in the immediate vicinity of the gate cathode junction, as I've indicated here. If that happens, most of the current will be breakdown current, and it will be situated just in the periphery region right here that I've outlined, and that current then that was pulling stored charge from the center in the direction that I've been indicating here in this diagram here, going this way, if all the current density gets concentrated in the periphery, then the interior here will not be affected by that breakdown by the gate current, and thus will remain with a lot of excess stored charge in the base region here that won't be pulled out by a negative gate current, and thus the only thing that can happen in that case is these carriers will disappear just by normal recombination, and that will be a significantly longer time than if we were pulling out the charge by means of the turn-off gain. So in order for that to happen, we have to keep the gate current less than some maximum value that avoids breakdown, and thus we come up with the result that the anode current maximum that is controllable has to be less than the maximum allowed gate current times the turn-off gain of the transistor. We'll talk a little bit more about this possibility of using breakdown or having a larger gate current than we would normally expect to avoid breakdown in order to turn off the device extremely fast. The next topic to take up is the waveforms that we develop because of the turn on and turn off procedure. In order to describe the turn on and turn off waveforms, we need to consider the GTO embedded in a specific circuit, because depending on the type of converter that it is in, the turn off and turn on waveforms may be somewhat different. I've chosen to talk about a fairly generic circuit, a step-down converter, using a GTO. And the thing we have to realize about a GTO, it's a medium to high power device where the electrical stresses are going to be relatively large, and where other solid-state devices that are used with a GTO might be relatively slow themselves, such as the freewheeling diode. And so the GTO is probably going to need some kind of external protective measures. So I'm going to talk about the GTO in conjunction with this circuit, where we have both a turn-on and turn-off snubber. The turn-on snubber will limit the overcurrent from the freewheeling diode, and this part of the circuit is your turn-on snubber. And we'll also have a turn-off snubber to limit the rate of rise of voltage, to reduce the possibility of retriggering the GTO into the on state when we're trying to turn it off. And the turn-off snubber is this part of the circuit that I've shown here with a dotted circle. I'm including a little bit of stray inductance as part of the turn-off snubber because inevitably there is going to be some. And so we'll attempt to describe the turn-on and turn-off waveforms in the presence of these snubbers. First, I'll look at the turn-on waveforms. I imagine that I have a gate current here at the top of the picture that turns on extremely rapidly to a fairly large value, I sub g, and after a specified period of time that I specify as TW, which we know guarantees that the device is on, we may back off on that current to the so-called back porch value. We need to keep some current, some minimum gate current flowing into the thyristor for the entire on time to make sure that some of the cathode islands don't drop out of conduction. As a result of this positive gate current, the anode current initially doesn't turn on. There's a turn-on delay time before the anode current begins to rise, and that's the amount of time it takes in our two-transistor model for enough charge to be inserted into the bases of transistors to push them into the active region, where then the self-latching feature of the GTO structure comes into play. When that happens, then the current rises very rapidly, and it actually overshoots the final on-state value. That overshoot is due to the freewheeling diode recovery current, which adds to the normal on-state current that we'd have in steady state, and so we have that current overshoot. The anode voltage begins to drop precipitously at the same time as the anode current begins to rise, and the reason for that initial drop is due to the inductance of the turn-on snubber. At the time the freewheeling diode current reaches its reverse maximum, the rate of change of the anode current then is much less than it is in this steeper portion, and so the inductance is no longer effective, and we still have some finite voltage larger than the on-state voltage still in the anode to cathode voltage. There is a small rise in that voltage because of the inductor no longer blocking the voltage from the power supply, and then as the current goes from its peak down to the steady state value, there's a small drop in voltage until we get to the on-state value of the anode to cathode voltage. In conjunction with that, the gate to cathode voltage precipitously goes from its, or very rapidly goes from its reverse bias value to the forward bias value, and then as the gate current drops to its smaller value in the back porch region, the gate to cathode voltage will also drop somewhat. Now, turn off is analogous to turn on, just the inverse, at least qualitatively speaking. Going to the, oops, I went too far on my slides. Here are the turn-off waveforms. The anode current, the gate current begins to go negative. It takes a finite amount of time to reach its positive value. There's a turn-on or turn-off delay time, T sub S, or storage time, before the anode current begins to drop, and that's the amount of time it takes to pull all the excess charge out of those two transistors until one of them enters the active region from saturation. There is then a fairly rapid drop in the anode current as the current gets commutated from the GTO to the capacitance of the turnoff snubber. Initially, as the anode current begins to drop, there's a rapid rise in the voltage between anode and cathode, and that rapid rise is due to the stray inductance that I showed in the circuit containing the turnoff snubber. And then when the current flattens out, the voltage will drop a little bit, and then the rate of rise of the anode to cathode voltage is going to be controlled by the turnoff snubber, mainly the capacitance, and it's kept below some maximum value that is specified on the specification sheet of the GTO. The gate to cathode voltage initially stays positive, and then about the time the anode or the gate current reaches its maximum, there's a rapid change in the voltage going from positive values to large negative values. And in fact, that stray inductance, or maybe even a purposely inserted inductance in the gate drive circuit, may be inserted in order to guarantee that for a short period of time we break down the junction in order to maintain a large current flowing in the negative direction through the gate, and that is the region labeled here T sub W. During that time, if we didn't have breakdown and we kept the anode and the junction then became reverse biased, then there would be no current being able to flow out the cathode. It would all have to flow out the gate, and so the current that is pulling stored charge out of the thyristor would be limited by the value of the gate current, and we would normally know that gate current value would be several times smaller than the peak anode, than the steady-state anode current, because we are trying to make use of the turnoff gain. And because the turnoff gain, in that situation where we no longer have anode current flowing or cathode current flowing, all the anode current flowing out of the gate means that we're going to have a relatively long time to pull that stored charge out, and hence the so-called tailing time that I show on the waveform for the anode current in this region right here. And the problem with that tailing time is it lasts a fairly substantial amount of time compared to the rest of the switching times at turn off, and leads to relatively high power dissipation because that current is still a substantial fraction of the anode current, 5, 10, 20% of it, and in the same time the anode to cathode voltage is fairly large, and so this leads to undesirable power dissipation that we would like to minimize if possible. Well, one way of minimizing that tailing time and thus speeding up the total turn-off time to shorter times and minimizing the power dissipation, that switching loss in the tailing time interval, is to use what is called a unity gain turnoff of the GTO. When we rely on the turnoff gain, this leads to undesirably long turnoff times because the gate current is only a fraction of the anode current, and it's the gate current that's pulling that stored charge out. If we could make the gate current equal to the on-state anode current, we would have a much larger current pulling the stored charge out, and thus we would minimize that time it takes to pull all the stored charge out. So, people have been investigating, and we've developed a couple of derivative devices that actually make use of having a turnoff gate current that's equal to the on-state anode current, a so-called unity gain turnoff. And so the overall turnoff times and the turnoff delay times are significantly shorter. In order to do this, we have to implement a specially designed turnoff circuit, gate drive circuit. It has to provide very large gate currents, at least for equal in time, in duration, for that turnoff times that we would expect to be able to have with this kind of circuit. The gate circuit stray inductance must be kept very small in order to limit the rate of rise of the change in the off-state or negative gate current, so that we can get the large negative gate currents very rapidly. The IGCT and the emitter turnoff thyristor both make use of this idea, and I'll describe each of those in a little bit more detail. Going to the IGCT, or integrated gate commutated thyristor, its unique features are, first of all, that the turnoff gate current is equal to or even greater than the anode current. The device chip for the GTO is integrated into the gate drive circuit. That is, it's put directly on the circuit board that has the rest of the external drive circuit. The cell size of the IGCT is somewhat smaller than the GTO to increase the amount of interdigitation and shorten the distance between the center of the gate and the center of the cathode metallizations. The gate metallization is done in a circular fashion, crudely as I've indicated here, where the connections to the outside world are from this periphery, as I'm indicated by the jumper wires, if you like, that I've indicated here. The advantages of this particular arrangement are much less gate drive stray inductance, so that we have a very rapid rate of rise of the negative gate current. Faster turnoff than the GTO, overall lower losses because of the shorter turn on and turn off times, and a higher VDT rating than the GTO. And in particular, in general, no snubber circuits are needed with the IGCT. The IGCT circuit symbol is a little bit different than the thyristor. The gate structure indication here that I've circled is a little bit different than it is for the standard GTO. An example of an IGCT is shown here on the next slide. You'll note here's the circuit board, here's the external drive circuitry right here. Here is the GTO itself, or the modified GTO circuit. And I guess it isn't showing up very well, but I'm trying to draw a line indicating this circular area here where the GTO is. It's a specially designed GTO with a low inductance gate drive circuit. The ratings of this particular one that I picked out of the literature is about 4,500 volts blocking, controllable anode current, on-state current of 4,000 amps, and average forward current of 1,200, and switching times of 10 microseconds or less. On the right, I show the approximate drive circuit. There are two main sections, the turn-on section in the upper part, and the lower part is the turn-off section. And in particular, shown here with a circle around it, is a very large capacitor bank for providing the large negative gate currents on a transient basis. In this particular example, it's about 50,000 microfarads. This drive circuit can provide on-state currents of 500 amps positive gate current for 10 microseconds, and off-state currents full forward equal to the full forward current for at least 10 microseconds, and very low series inductance, 3 nanohenries or less, in the gate drive circuit. The IGCT is similar, but to the next device I'm talking about, and this one is the emitter turnoff thyristor. Here the basic idea is we will use a GTO and in series with it put on a turn-on MOSFET in series with the cathode. In parallel with the gate, I'm going to put a P-channel MOSFET and connect it to then what I'm labeling down here as the external cathode. The way it works is we'll apply a positive gate pulse at the gate cathode terminals to turn on the N-channel MOSFET and turn off the P-channel MOSFET. That turns on the ETO. And the way that occurs, of course, is by turning off the P-channel MOSFET, I'm going to be applying a positive gate to cathode voltage. And I'm creating at the same time a short between the cathode of the GTO itself and this external cathode. So that's what I would need to do to turn on even a standard GTO, is to implement that equivalent circuit. To turn it off, I apply a negative gate pulse to the same terminals. I turn off the turn-on MOSFET, the N-channel MOSFET, and I turn on the P-channel MOSFET. By turning off the N-channel MOSFET, I allow the internal cathode, or if you like, the cathode of the GTO itself, to rise above the external cathode voltage. And at the same time, I'm shorting the gate down to the external cathode. And so I'm applying then a negative gate to cathode voltage, and I can control what that voltage is by means of the MOSFET and probably some kind of resistive divider circuit that applies a known voltage across the off-state N-channel MOSFET. The overall circuit symbol for the ETO is shown here, and there's usually two terminals brought out, one for the turn off and one for the turn on. Its overall performance is similar to the IGCT. However, the gate drive circuit for the ETO is somewhat simpler. It's easy to parallel several of these N-channel MOSFETs, and it has a positive temperature coefficient so that it makes it easier for the parallel N-channel MOSFETs to share the current equally. And in addition, that series N-channel MOSFET can be used for overcurrent sensing. An example of an ETO is shown on the next slide. Here are several examples of commercial devices. And I need to go to the next slide, of course. And here are the examples I was talking about. The approximate drive circuit is shown. One for the turn on, one part for the turn on, one part for the turn off. And in general, turn on and turn off times of 10 microseconds or well under that. And so these devices are able to go to somewhat higher switching frequencies than a standard GTO. And these devices, probably in the not too distant future, all GTO and related devices may be superseded by IGBTs, especially those that are going to perhaps be made in silicon carbide, and I'll talk more about silicon carbide devices in a separate video. Thank you.